All right, folks, these are the answers to 2012 number 3. And this is one of the few torque and slipping problems that we actually have an average for. And it's a low 2.71 out of 15. The average for all of the ones I have is like 6.5. So this is about as low as it gets. Now, notice it is the third question. So sometimes it's just that people run out of time. So this is probably a combination of it's not a straightforward problem, and it was the third question. So this is really, really similar to 1980. That was the previous question from the Google Doc, but more is helpful in case you need it. So you have a ring. They give you the rotational inertia for the ring. And it is sliding with a constant velocity v naught. And then it runs into a rough surface, and then they restart the clock to be t equals 0 when it hits friction. And then it will slide and rotate, but that friction will eventually start rotation, cause rotation, and at some point it will turn into no slip. Okay, so I'll let you look at the picture more if you want to, and express all answers in terms of the following variables. Fundamental constants for you all is just going to be G. And okay, so question A. Starting from Newton's second law in either translational or rotational form as appropriate. Derive a differential equation that can be used to solve for the magnitude of the following as the ring is both sliding and rotating, so in what we would call period 1. Don't freak out about differential equation. We will do, hopefully, that at the end of the year. Even if you never learn that in calculus, hopefully you'll know enough to tackle that on the AP. But they're giving you a hint. You're going to start with Newton's second law. All right, so don't panic about what you don't know. Focus on what you do know. So we want to find the linear velocity as a function of time, but we want a differential equation. So I'll give you a hint. Anytime they say differential equation, it means F equals ma, and then and they're trying to get you started on that front using Newton's second law. That is Newton's second law. It feels more like a formula, but that is the second law. And clearly, since we want linear velocity, we're going to start with the translational form, and then in part B, or double I, we're going to do the rotational. So, starting from Newton's second law. Now, notice they didn't say draw a force diagram, which is unfortunate. Maybe they felt like there were already so many points to add up to 15 that they didn't have the point value. But whenever you find yourself writing down sigma F equals ma, draw a force diagram so you don't make a mistake. So this is the ring. Velocity is not a force. So if it were a force diagram, don't draw that on your diagram because the AP doesn't like that. The ring has a weight, and it has a normal force. This is a boring problem. Those two are equal. And oh, we want it, I'm sorry, I think I said period 1. We want it in period 2 in the transition period. So without friction, it will start to skid along the floor and the nooks and crannies will catch, right? So the initial velocity is V naught. The nooks and crannies will catch, and that will cause, I'm just going to use lowercase f, kinetic friction. All right. So technically, you've got both vertical and horizontal forces. This is a boring problem. The normal equals the weight, so I'm not going to take up time with that. So we have horizontally, so I'm just going to put subscripts on this. Some of the forces in the x direction equals max. All right, let's call to the right positive and to the left negative so we can see that friction, it needs a negative sign in front of it. So we have minus kinetic friction equals ma. What is the formula for friction? Mu times the normal. What is the normal force? it's equal to mg. I'm not going to take up the time to show that. I'll do it real quickly. Sum of the force in the y direction is 0, so normal minus mg equals 0. I don't think, I'll double check, I don't think you needed to show that to get the points. And then you see that the mass cancels. So the acceleration is minus mu g. Now you might say, like, that's not a differential equation. You may not know what a differential equation is. And again, I don't think the AP should have differential equations on it. Calculus, yes, but differential equations, no. Because you don't tend to take that. Like, anyway, I will stop giving you my opinion. All right. A has a fundamental definition. What A is equal to is the derivative of velocity with respect to time. And this right here, as soon as you turn A into dv dt, that is a differential equation. What that means is there is some function, v as a function of t, that when you take the derivative of it, you get minus the coefficient of friction times g. So to me, a differential equation is kind of like a puzzle. It's saying, let's see if we can figure out what function satisfies this relationship. And we're going to solve it later on, but this is all you need to do. And so you might, like, turning A into dv dt means that you have now made a differential equation. Okay, and that was 3 points. So if you did this, you beat the average. So I'll quickly go over where the points were, because since this is more recent. So you got a point for saying F equals ma with friction as the net force. You got a point for understanding that friction was equal to mu mg. And you got a point for saying acceleration is dv dt, which again, I know that some of you may not understand that yet, that's called a differential equation. Okay, so that's where the 3 points were. And then, again, Cammie's not liking my omegas, but now it's confusing, but now we're going to start from Newton's second law in the rotational form to derive a second differential equation. All right, so now we're going to say the sum of the torques equals I alpha, because they're saying start with Newton's second law now in rotational form. So let's go back to this picture so we have more room. This is our pivot point. The normal force passes through the pivot so it doesn't cause any torque. The weight starts at the pivot so it doesn't cause any torque. The only thing causing torque is that friction. So you have RF, and I'm just going to define the way, I'm going to just say winning minus losing. So I'm going to make that a positive torque, equals I, and I, since it's a ring, is mr squared alpha. Okay, and the force, the one force that's causing torque is friction, and we already showed our work that friction was mu mg equals mr squared alpha. Sorry, these m's are the same. They don't look like they're the same. M's cancel, one of the r's cancels, and so you get alpha equals mu g over r. But that's not a differential equation yet. You need a derivative, and so d omega dt equals mu g over r. That's the differential equation. There's a hidden derivative inside this alpha. Okay, and then I'll quickly tell you where the points for that are. So you got a point for saying sum of the torque equals I alpha, and substituting this for I. So it's kind of like this and this together were worth 1 point. You got a point for calculating torque correctly. which I'm sorry, that's not it because I didn't plug in for the, you got a point for calculating torque correctly. And then you got a point for replacing alpha with d omega dt. Okay, so that was another 3 points. So then if you got both of these, you are at 6. You're at twice the average. Okay, so they tried to help you out a little bit with saying you're using F equals ma or torque equals I alpha. All right, now it gets a little tricky. So I'll try to do this slowly because some of you have not seen this before. Derive an expression for the magnitude of the following during that transition period. The linear velocity as a function of time. Okay. If you don't know how to solve differential equations, you had one option. This is worth 2 points. So option number 1 would be to say, you know what? My force diagram was not changing with time. So I know my acceleration is constant. It did have an initial speed. My acceleration was minus mu g, I believe, t. Done. Okay, so this would be 1 point, I think, for recognizing, hey, I can use physics Sudoku because the acceleration is constant, and then 1 point for pulling down the information you needed. Okay, the other way to do it, and I'm just showing people so that you understand what they mean by differential equation, is saying we knew that a dv dt was a minus mu g, sorry, just minus mu g. Let me do that a little neater. That mathematicians hate this because this is an operator. This is a derivative. It is not a fraction, but physicists do this all the time. We say, you know what? I'm going to multiply both sides by dt. And now I'm going to integrate both sides. What's a little tricky in physics is it works better if you integrate, instead of using an integration constant, if you integrate using your initial and final conditions. So I started with an initial speed v naught. So instead of integrating from a to b, I'm integrating from v naught to some arbitrary v. And mathematicians will also say you can't have this variable be the same as that variable, but physicists do it all the time, sorry. The nice thing about dt is we can start the clock at 0 at the bottom of our integral, and we're going to go to some arbitrary time. Again, mathematicians don't do this on the calculus AP. They don't like those two variables to be the same. We don't care. Okay, if the integral of dv is just v, you can think of this as like v to the 0, which is 1, and then you add 1 to that, which is just v to the 1. But you have to evaluate it from the two endpoints. And then, sorry, I'm running out of space. And then minus mu and g are all constant, so we can take that out of the integral. And then let's change color pen so we can see what's going on. We're going to evaluate v from v to v naught, or from v naught to v. So you remember it's the evaluate the function at the upper endpoint minus lower endpoint, so you get v minus v naught. And then same thing we did with the dv. This is really t to the 0. So I have the minus ug out front, and you add 1 to the 0, so you get t to the 1 divided by 1. And then we're going to evaluate that from 0 to t. So we get v minus v naught equals minus mu g t minus 0. And then we want to solve for v as a function of time. So we're just going to add v naught to both sides. So you add v naught to both sides, and you get this, which I erased what we had up there. But again, this is just v equals v naught plus at. This is just showing you how you get that from calculus, from solving a differential equation. Okay, and then that was worth 2 points. From the calculus point of view, you got 1 point for getting to this point right here where you had an integral on either side with appropriate limits. and then you got another point for going through the calculus to solve that. So that was, you had to work harder for the 2 points in this method versus the constant acceleration method. Okay. Letter I, the angular velocity is a function of time. Really, really similar situation, so I'll go through it more quickly. We know d omega dt equals mu g over r. So again, multiply both sides by dt, so you get d omega equals mu g over r dt. These are all just constants too. And then we're going to, we want to add up all the little bits of d omega, and it started with no initial rotational speed, so that's easy. So these integrals are a little bit easier. And then integrate all the little bits of dw, and you get w evaluated from omega to 0, so that just turns into w. You can pull this out of the integral because it is a constant. So you get omega equals, if you add up all the little bits of t, or again, this is t to the 0, that gives you t evaluated from 0 to t is just t. So what you get is omega is increasing at a uniform rate. I believe this was also worth 2 points. Okay, so that's how you solve the differential equation. You could have also said, hey, my torque is constant, so I'm going to use omega equals omega naught plus alpha t, and omega naught is 0, and alpha is ug over r times t. All right, moving on. I found this when I first did the key to this, the year that this AP was. I found this really tricky because I find this a really, really weird misdirect. So I liked, if you've done the 1980 slipping, turning into no slipping, I felt like that part was phrased better, because this distance L is kind of, it's a red herring. You don't need L at all. The important thing is not that it's traveled a certain distance. So that makes you think about work and energy. Oh my God, what is that L doing in there? Or maybe I need to use the position function. Really, really, I don't like it. I think it's sending you down the wrong path. I wish they had said, find the time it takes to transition from slipping to not slipping. So again, that L is irrelevant. What is important is that at distance L, it starts to not slip. And so what is happening is the linear speed is decreasing because of friction, and the rotational speed is increasing because of friction, because friction's causing a torque. We didn't talk about that before, and there's your lever arm. Here's friction. Friction is making that rotate. If this is a bird's eye view of a merry-go-round or a pottery wheel, and you start, kicking on it with your hand, which is really just friction, you're going to make it rotate. And so V goes down and omega goes up, and at some point, which they satisfy the relationship of not slipping, and then that point that it's touching the ground is instantaneously at rest, and it stays not slipping. So you don't get any more, then it turns into static friction, not sliding friction, and you don't have any more energy loss, and this maintains this situation. Okay, so I really hate that, but I'll stop that now. Okay, so we want to know the time at which this happens, and that's why they were kind of priming you for, this is my velocity as a function of time. Let's plug that in. My velocity is v naught minus mu gt. My omega as a function of time is mu g over rt times r. And then, nice, these r's cancel, and you get v naught. Let's add that to the others, to both sides. So you get V naught equals mu GT plus mu GT, or V naught equals 2 mu GT. And solve that for T means time equals V naught over 2 mu G. All right. I said this in 1980, but in case you're just seeing this, doing this one, check your work. It should make sense that as V naught is bigger, it's going to take longer to decrease V enough so that V and omega have this relationship. So as V, the faster it's going, the longer it's going to take to stop skidding. And it should make sense that the bigger the coefficient of friction, the more you can lock on, and the greater friction is going to be, the more torque you're going to have, the faster omega is going to increase, so that this can be true. So if friction is bigger, it's going to take less time to stop skidding. G might seem a little confusing because you're like, what is freefall doing in there? G is because friction is mu mg. So as G increases, the nooks and crannies are squished. They're locked into each other. So mu is making more nooks and crannies, or more rough nooks and crannies. G is squishing, interlocking them more effectively. Both of these are going to increase friction, which means your omega is going to get up to speed to match V quicker. Okay. So that is the time. I think that was worth 2 points. And so it was 1 point for understanding no slip, and then 1 point for pulling all of it, understanding that you needed to substitute that V was actually a function and omega was actually a function. All right, question D. Derive an expression for the magnitude of the velocity immediately after it has traveled the distance L. Sorry, I'm trying to find my key here. Yeah. So we know that V equals V naught plus AT, and we just found the time. So this is pretty plug and chug. A was minus mu G, and T was V naught over 2 mu G. So this is V naught minus V naught over 2. Oops, sorry. I was trying to show you this stuff cancels. So a full V naught minus a half a V naught means the speed has been cut in half. As it was kinetic friction, slowing it down, the speed was cut in half, which makes sense, right? It's slowing down. Not that necessarily that it's a half, but that this is less than that. That was worth 1 point. I wish instead of doing that, because you already proved that you understood that relationship before, I wish that they'd taken that point to say draw a force diagram, but I'm not the queen of the world. Okay, thank you for your patience. We got one more question. Derive an expression for the distance L, and that is worth 2 points. I think that's maybe why they had that distance L there to begin with. So there's a lot of ways to do this. The PDF answer key that's linked shows you a bunch of them. 2 of them involve physics Sudoku. Okay, one of them is don't know, don't care, and the other is using the position function. Right, I'm going to let you dig through that yourself. They're all legit. They're all legit ways to get the 2 points. But the one that I want to go through, because we haven't practiced a lot of calculus, is to find the distance traveled, it is the integral of the velocity with respect to time. Just like velocity is the derivative, that makes sense, and then the position is the sum of the or the integral. Time starts at 0, and it's going to end at v naught over 2 mu g. We could say t2, I'm running out of space, or whatever, transition, it's a specific time. So what I see in physics, and I'm not dissing the math department, is in math, I think in general, they tell you, here's my lower limit, here's my upper limit. In physics, you have to figure it out. That's what's hard. We can decide that the time t equals 0 and t2 is defined as v naught over 2 mu g. So you could put that in your upper limit. I was just running out of space, and it's a little bit more efficient to do it this way. Okay. Do not say that the integral is v squared over 2. That is not true. That would be the integral of t dt. Okay, this is v, and v has a hidden function of time. What is v? V is v naught minus mu g t. Right, so you have to, this v has a hidden function in it. Where do we get that? Right here. And now I can do this integral because the variables match, right? My function isn't hit like this. These are matching, whereas these are not matching. I don't know what the technical word for that is. Okay, so then this is the integral of v naught dt from 0 to t2 minus, and I'm just going to pull out mu g because that's a constant, minus mu g from 0 to t2 t dt. Okay. Oh, I should have pulled out v naught too. That's a constant too. So this is going to be v naught. And they're the same limits. I separated them out just because I'm not sure where people are in their calculus, if that makes it look easier. But we have v naught minus mu g. Oops. Sorry, I'm going on autopilot, and I didn't make the paper answer to this. Okay, v naught t minus mu g t squared over 2. But we need to evaluate that from 0 to v naught over 2 mu g. Okay, so they're really making you work for the 2 points. So L equals v naught times v naught over 2 mu g minus mu g over 2 v naught over 2 mu g quantity squared, and then we have to subtract the value of this function when you evaluate at 0, but that's going to go away and that's going to go away, so it's minus 0. Okay, so then this is v naught squared over 2 mu g. No, it's, sorry. No, this is, sorry. There is a minus sign there. I want this to not be negative, but I think we're okay. So this is minus mu g over 2 times v naught squared divided by, you got to square everything, divided by 4 mu squared g squared. So this is, so this will cancel with one of these, leaving you with v naught squared over 8 mu g. All right, so now I'm happy because I have the same, like these match almost. So we need to find the common denominator of 8. So multiply that by 4, multiply that by 4. So you have 4 of this stuff minus 1 of this stuff equals, sorry, I'm out of space, equals 3 of that 3/8 V naught squared over mu G. Whew. And that is the length. So that's why they had the length in there. A lot of work, but again, I wanted you to see the how and when you use calculus, but you could have absolutely used any of the physics Sudoku constant acceleration equations because acceleration was constant. All right, so again, go to the PDF if you want to see that. So this was a challenging AP. One quick last warning or hint, you know, in the past, the averages is 66%. So don't get discouraged. I want you to think about if you have done enough studying to take the AP, but don't get discouraged and think that it's all or nothing. Like, one of the things you want to keep practicing as you get closer to the AP is fighting for points, just straight out fighting for points. And I think roughly a 3 is the average. So, right, if you got 3 of these points, you would have gotten a 3, a number 3 on the AP. And then, you know, 3 more of the points would give you a 4, and maybe getting 4 over the average would give you a 5. So don't feel like you have to get all of this to do well in the AP. But they're all good, deep thinking questions for you to learn more about. All right, that was a lot. Thanks for listening.